yeah, so, and then really the remaining part is, so let me just draw a line here. So the remaining part is to prove the final result in this chapter, which has something to do with the involutive automorphisms of your early algebra, because the idea is that, so you know how we know that the conjugacy classes by inner automorphisms or by all automorphisms of real structures on G are in one-to-one correspondence with conjugacy classes, again, by inner or all automorphisms respectively, of involutive automorphisms of G. And we know the correspondence. It's pretty much the main step is just composing your involution or your real structure with some fixed compact real structure. And then, so if you want, for example, to classify all real semi-simple Lie algebras, one way to do this is to use the classification of complex semi-simple Lie algebras and to classify on each of them, on each of those simple Lie algebras anyway, to classify all possible real structures, because any real semi-simple Lie algebra can be obtained. It's pretty much a complex semi-simple algebra plus some fixed real structure. So, and this is the same as to classify involutions. So really you want to have some understanding of what is the general form of an involutive automorphisms, of an involutive automorphism of a complex semi-simple algebra. And this result kind of gives you a lot, not the full answer, but it gives you, brings you way closer to kind of that understanding. Before we formulate and improve it, let me just say one thing. So suppose I give you G complex semi-simple. You can see what I'm writing, right?
Yes.
Yes.
Mm-hmm. Cool. So I give you this and I fix some compact real form. Let's say fix compact real, form G0 of G. Well, you know what? Let's just first go the other way around. Suppose you have G, and you take a Cartan subalgebra. You make a choice of positive roots. You fix canonical generators. So you have EIs, HIs, and FIs. And then using them, you construct in our canonical way this compact real structure. Remember that it's the one that sends EI to minus FI, FI to minus EI, and HI to minus HI. There is a unique real structure, so it's C antilinear, that looks like this in the canonical generators. And I think we denoted it as, so we have this, we have this, we have delta plus, we have EI, FI, HI, and then we have, I think we denoted it as tau, sends EI to minus EI, FI, sorry, minus FI, FI to minus EI, HI to minus HI. This is a compact real structure. And then, so if this is a compact real structure, you can look at the set of points that are unmoved by that compact real structure, and this will be a compact real form. So we can say that it's G0. And then you know that the intersection of your Cartan subalgebra with that compact real form. So your Cartan subalgebra is decomposed as the R linear span of all root vectors, not of roots themselves, but of the dual notion of root vectors. We call this HR. And then that will be a real part. And then there is the complex part, which is just I of that. So it's easy to just from the way your tau is constructed, it's easy to see that the intersection of H with the compact real form is IHR. So you can pretty much see that on the, well, just because on HR your compact real structure is -1, so it has to correspond to minus. The intersection where it's 1 will be IHR, not HR. So what I was going to say is that you can go in the opposite direction. So here you started with this H and delta plus and canonical generators, and then you define the compact real structure, and then you notice that the intersection of your Cartan subalgebra with G0 will be IHR, and this will be a maximal torus. This is where maximal abelian subalgebra of G0. So maximal abelian subalgebra of G0. What I was going to say is that you can go in the opposite direction as well. So you start with, as I said, so you start with G, you take any compact real form G0, and then suppose you take a maximal torus in G0. So take H naught in G naught maximal torus, so maximal abelian subalgebra. Claim, then H naught C, which is just H naught plus I H naught, is a Cartan subalgebra of G. Well, let's briefly prove this. It's easy. First of all, let's show it's abelian. Well, that's obvious. H naught is abelian, so its complexification is abelian. Next, let's show that it consists of semi-simple elements. So it will be a toral subalgebra. So the way you do this is, remember that I think it was chapter 3. So we had this thing that whenever you have a real structure, in our case it's tau, you can associate a Hermitian skew, Hermitian sesquilinear form, or like three and a half, like 1.5 linear form, whatever it's called, on the Lie algebra. I think we denoted it as H tau. It was defined as minus B X tau Y. So this is Hermitian 3.5 linear form. And on the degenerate one, and then there was a claim that this thing is, it doesn't matter here, but in any case, this thing is actually a Hermitian inner product, so it's positive definite, if and only if your structure is compact. In our case, it's compact, so this is an actual Hermitian inner product. And there was another statement, it was easy, that for every X in the real form corresponding to that real structure, so in this case, in any X in G0, the adjoint is skew Hermitian on G with respect to your Hermitian inner product. That was one of the statements in chapter 3. In particular, is diagonalizable. the adjoint of X is diagonalizable with, well, it doesn't matter, but in any case, with imaginary, purely imaginary eigenvalues. Like all skew-Hermitian operators are. So now we want to show that any element of this thing, of the complexification of H0 is semi-simple. So it looks like this. Take Z in this complexification. You can write it as X plus IY. Then X is diagonal. The X as the adjoint of X as an operator on G is diagonalizable, so semi-simple. The adjoint of Y as an operator on, or of IY, it doesn't matter, as an operator on G is diagonalizable, therefore semi-simple. But their sum, why is it also diagonalizable? Well, because X and Y, or X and YI, commute, because H0 is abelian. So their adjoints also commute. So you have two commuting operators which are diagonalizable. So they can be diagonalized by linear algebra in the same basis. And in this basis, X plus IY will just be also a diagonal matrix. So let's say like this, X and Y are diagonalizable in the same basis. Therefore, so is Z. Therefore, Z is semi-simple. Okay, and now we have to show that now we know that this is a toral subalgebra, and then we need to show that it's a maximal toral subalgebra. Well, this is easy. Note that H0 C, the complexification, is just the centralizer in G of H0. Why so? Well, this follows from the fact that tau is a real structure. If you have some element of G that commutes with the whole H0, then you can decompose this element as X plus IY, where X is in G0 and Y is in G0. And because of this, both X and Y will have to commute with H0. So the centralizer is necessarily something in G0 plus something in IG0. Well, and from there you can easily see, so let me just kind of make this in bullets. So indeed, the centralizer has to be of the form A plus B, where A is in G0, B is in IG0, and then and then H0 is maximal, abelian in G0. Therefore, A has to be, well, H0, and B has to be I H0. Therefore, the centralizer, well, it's just H0 plus I H0, which is what we wanted. So your complexification is just the centralizer of H0. Now, if you have any other toral subalgebra containing H0, the complexification, it will have to lie in the centralizer. So it cannot be strictly larger than the complexification of H0. So therefore, this thing is a maximal plural subalgebra. Are there any questions about this lemma, this claim? Are you still with me?
Yeah.
Okay, good. Okay, so now we can formulate the main proposition. So suppose I give you G complex semisimple, and then I give you theta an involution. Then, one, there exists a Cartan subalgebra H, and there exists a choice of positive roots in the corresponding root system such that theta is not only some automorphism, but it is an automorphism that fixes H and the positive Weil chamber. I think we denoted that thing as the normalizer of H and N. This was a notation that I used, so let me just kind of reminder. So what Onishchik calls automorphisms of GH, I call, just because it's kind of more standard, just normalizer of H, those automorphisms of G that preserve H, and then what he calls odd GH where here P is just the set of simple roots. I call, and again, it's kind of more intuitive, I think, the normalizers of H and N. These are those automorphisms that both preserve H and preserve the sum of positive root spaces. This is the same thing as to say that the corresponding kind of permutation of roots preserves the set of simple roots or of positive roots. That's the same thing. So we can always, for any involution, we can make such a choice of H and delta plus that this involution will lie in this normalizer. Okay. So now recall that, again, it's another piece of reminder. We had the following thing. We had these two groups. So this is this normalizer. Inside of it, we have those automorphisms that fix H pointwise. They will obviously fix the set of positive roots as well. That was explained back then. And so from here, we had this, I think I denoted it phi prime representation or group homomorphism, which we proved was surjective, into the automorphism of the Dynkin diagram, which I denoted as dt. Well, basically, if you have such an automorphism, then it permutes the simple roots. So that will be your automorphism of the Dynkin diagram. And from here, we constructed a section of this map. I think we denoted it as psi. So this psi sends an automorphism of the Dynkin diagram to S hat, which is just defined on the canonical generators in the same way that you permute your simple roots. If you send alpha I to alpha j, then S hat will send EI to EJ, hi to hj and fi to fj. And this will give you uniquely an automorphism of G that will preserve both H and N. So this was a section, and there was a claim. One of the main things that we proved, that so now inside here, inside this normalizer, you have two subgroups. You have this subgroup, which is abelian and nice. It's kind of like a torus, abelian torus. And you have this, the image of this embedding. And the claim was that this is a symmetric product decomposition. G Hn decomposes as the centralizer and then this the image of psi. That was the reminder. So in particular, if you know that your theta lies in here, then you can also decompose it as something here and some as hat. But claim in 2 is actually more. We claim that not only it can be decomposed like this, if we conjugate theta by some inner automorphism, well, that actually lies in here, or sorry, in here, then we can make it even nicer. Theta is conjugate by some inner automorphism to something of the form, well, let's call it theta 1. I think let me just follow the notation of Onishchik. So he denotes it as psi s hat, where s hat, well, where s is some automorphism of the Lincoln diagram, and psi can be written as the exponential of add of pi over 2 it, and t lies in RH, and alpha of t is an even integer for every root alpha. So here's the thing. You have, let me make it to the third piece of reminder, just because it was so long ago. You have H. This is a abelian complex Lie algebra. So if you look at the corresponding subgroup of the automorphism group, so your G, you can identify it with, so let me just say that, like, let me make it more lucid. You have G, you have the adjoint map, and then here you have the group of automorphisms. This is the identity component of the whole automorphism group. And here you have H. So the idea is that H will, under this identification by the adjoint representation, H will correspond precisely to that centralizer. That was part of what I proved last time. So if the group, this centralizer is precisely elements of the form the exponent of the adjoint small ad of something from H. So in particular, this guy is just some specific element of this centralizer. The point here is that we can make it some very special element, not just some X of adjoint. We can have this condition. Okay. And then 3, theta 1 commutes with all structures that we have. It commutes with the compact real structure tau. It commutes with the split real structure sigma, and then commutes with the Weil involution omega, which is just the product of these two. So let me just say that this is compact, this is split, this is Weil. They're defined on our canonical generators because everything is fixed. Okay, so this is the statement. Basically, it means that if you have an involution, all involutions are of very nice form given here. You can pretty much think of them as this theta 1s up to conjugation. Okay, any questions? Okay, then let's prove it. So let's make it a proof. So first we will show that we will prove 1. So we will show that there exists a Cartan subalgebra, which is invariant under our theta. So there was one of the statements in chapter 3 where you can show that for every involutive, if you have a fixed compact real structure, and then you have an arbitrary involutive automorphism, then that involutive automorphism can be conjugated to some other involutive automorphism that now commutes with your compact real structure. That was part of our big theorem about the one-to-one correspondence between real structures and involutions. So take any compact real structure, tau. We know, this is a proof of 1. We know that theta is conjugated by inner automorphisms, but this is irrelevant, to something that commutes with tau. That is, well, let's say, I don't know, let's say f theta f inverse commutes with tau. Well, let us just replace tau, which we just took randomly, by f inverse tau f. So we can think that just theta commutes with tau. Okay, and tau is still a compact real structure. Now, because tau commutes with theta, let us write G as G naught plus I G naught, where G naught is just the set of the corresponding compact real form. from here, G naught, so theta of G naught is G naught, because theta commutes with tau. Therefore, we can decompose G naught as G naught plus and G naught minus. I think his notation is different, but yeah, maybe I can use his notation just so that it's easier for after that to follow if you want to consult the book. So let me say, let's call it not G naught, but U, just because Onishchik does so. Sorry about that. So let's call it U, and then IU. Here U is this. Theta of U is U. So U can be U plus and U minus. Yeah, and then also he writes them as subscripts and not superscripts. Basically, U plus is where theta is just identity. U minus is where theta is -1. This is an involution, so you have this decomposition, and this is a Z2 grading of U, meaning that if you take the commutator of U plus and U minus, you'll go to U minus, and then if you take the commutator of U plus and U plus, or U minus and U minus, then you'll go to U plus. Okay, so take A in U plus maximal abelian. Then let's do the following. Let's first consider I think he denotes this as, I'm going to write it as H naught. Consider H naught. This is the centralizer in U of A. So everything in U that commutes with A, just because this is a Z2 grading and A is maximal abelian here, this is really just A plus some B, where B is in U minus. Okay, so let's go further and consider H, which is just the complexification of that. So this is H plus H naught plus I H naught. Well, I claim, sorry?
Sorry.
So I claim that this, you can rewrite this as just the centralizer of A, but now in the whole G. Why? Well, pretty much for the same reasons. Because, again, the normalizer of G is decomposed into two parts. I think also let's say that, how should I put it? So, okay, so let's say this. G is decomposed as U and IU. Yeah, that's good. So H naught sits somewhere here. If you and then in turn, A sits somewhere in H naught. So if you take the of A in the whole G, and A sits here, it's the same as to take the centralizer of A in U plus the centralizer of A in IU. because you have the bracket relations between this summand and this summand. They're the same as in the for symmetric spaces. So, but now H naught is the centralizer of A in U, and the centralizer of A in IU obviously is just I H naught. So this is why we have this equality. Okay. So now claim H is a Dantzab algebra of G stable under theta, which is what we want. Okay, let's prove this. So we need to know two things: that this is stable under theta, and that this is a Cartan subalgebra. Well, note that H is just the centralizer of A in G, and A is stable under theta. But this is because U plus is stable under theta, and A sits in U plus. So if you have A stable under theta, then the centralizer of A will also be obviously stable under theta. Theta of A equals A, therefore theta of the centralizer of A will also be the centralizer of A. And this is H. So it's obviously theta stable. We only need to show that this is a Cartan subalgebra. But now we have this lemma that suppose we know that H naught is maximal abelian in U. We had this lemma here that in this case, the H, which is the complexification of H naught, will necessarily be a Cartan subalgebra of G. So we only need to show by the claim above suffices to show that H naught is maximal abelian in U. And then we're done. So we started with A, which was maximal abelian in U plus, but now we take A plus B, and then we want to show that this is maximal abelian in U, right? So let's show that it is abelian. First, show that H naught is abelian. Well, first of all, H naught is compact. Why so? Because U is compact. This is the compact real form of G. And then H naught is the centralizer of something in U. And if you look at the corresponding, if you take the corresponding compact Lie group corresponding to U, then the subgroup corresponding to this centralizer will be just a centralizer subgroup. So it will be closed, so it will be compact. You got something here? Well, yeah, kind of. Oh, that's, I guess, fine. Yeah. Sorry. So yeah, so H naught will be centralizer of something, so it's necessarily a compact algebra, complex algebra. So clearly, H naught is compact, and therefore reductive. So take the Levy decomposition. This is Levy decomposition. So because it's reductive, Z is just the center of H naught, and S is the commutator subalgebra, is semi-simple. In general, if this was a Levy decomposition, we would know that this is the radical, and it's just something solvable. But because H naught is reductive, then we know that this is actually the center. In particular, it's abelian. Now, H naught is the centralizer of A. Therefore, A lies in the center of H naught. Okay. But now, let me think. Now consider the following. So now we have the following computation. S is the commutator subalgebra of H naught. But we had another decomposition of H naught, which is A plus B. And here, A is abelian. And moreover, A is commutes with B as well. So this is the same as just the commutator of B with itself. Right? But then look, B, so A is in here, in U plus, B is in U minus. And the commutator of two things in U minus lies in U plus. So this thing lies in U plus, but also obviously it lies in H naught, because originally B lies in H naught. And so this is A. So now all of a sudden, S lies in something abelian, but it was semi-simple. So it is 0. Because it was semi-simple. Okay, so we know that we know that H naught is abelian, and it remains to show that it is maximal abelian. But this is easy because well, this is why. Because H naught is the centralizer of A in U. If you have anything abelian containing H naught, it will commute with A, so it will have to lie in the centralizer of A in U, which is H naught. So H naught is maximal possible. Since H naught is the centralizer, it is maximal abelian. Let me just move this and add the conclusion of the previous, sorry. Therefore, from here it follows that H naught is abelian. And then you have this argument that it's maximal abelian. Any questions about this part? Are you still with me?
Yes.
Okay. So we've shown that we found the Cartan subalgebra, which is theta stable. Now let's find the set of simple roots, which is theta stable. It's actually very easy. So another claim. Oh, before this, let's just note that. So you have, let's just see what we have. We have G. In this G, we have H. G is decomposed as U plus and U minus. H is decomposed as H naught plus I H naught. So as we noted before, HR will be the I part. HR is the real span of all root vectors. It will have to be the I part. So all the roots guys like H alpha are here in I H naught. Okay. So, and in here, let me kind of rearrange this. In here we had A, and so here we have IA. So claim IA has regular vectors. So vectors on such that no root vanishes in them. Proof of the claim. Suppose this is not the case. Assume all roots are singular. So assume that there exists a root such that it vanishes on the whole A. I guess in general, the claim that all vectors in A are singular means that for each element of A, there will be some root hyperplane containing it. But if you have some subspace, which is contained in the union of finitely many root hyperplanes, then it will have to be contained in one single root hyperplane, just because that's otherwise you won't be able to kind of fully cover your subspace, IA with those root hyperplane intersections. So this can be realized by single root. But then alpha of A is 0. But now, in turn, this means that G alpha is contained in this guy. Why? Because, which is H. Because how do you compute the commutator between elements of H and elements in some root subspace? Well, they basically just yeah, if you have H G alpha, let me write it like this. Then this will be just alpha H times G alpha. This is informal, but yeah. Therefore, if alpha vanishes in the whole A, then A will have 0 commutators with the whole G alpha. In other words, G alpha will be contained in the centralizer of A, which is our Cartan subalgebra, and this is a contradiction. So was there a question? I heard somebody saying something.
No, it was just me drinking water, sorry.
Sorry. Yeah, so this is contradiction. This cannot happen. So there exists a regular vector B in IA. We'll take the root chamber of V. Now, theta fixes A pointwise. So it fixes IA pointwise. Therefore, theta of V is V. Therefore, theta of D is D. So theta preserves both H and D. So which proves part one. Any questions so far? Good. This was the main part, really, the longest one. The second part is easier. So let's just go back. So we claim that theta now can be written as something in the centralizer of H times some S hat, and then such that this element in the centralizer of H has nice properties. So as I mentioned before, we know that we can write theta as phi S hat, where S is in the automorphism Lincoln diagram, phi is in the centralizer here. And remember that, as I mentioned, centralizer of H is just an abelian complex weak group of the form exponential of AD of some x, where x is an H. Okay. Also, theta square is identity. Therefore, well, look, this is the semi-direct product decomposition. Phi lies in the normal part, the centralizer, and S hat lies in the not normal part of the semi-direct product decomposition. So when you multiply two elements in the semi-direct product decompositions, the parts that lie in the normal part, the multiplication for them is difficult. It's some weird formula, right? But the parts that lie in the not normal part, that is here, the multiplication for them is straightforward. You just multiply those. So in particular, S hat square is also identity. Just because that's how you multiply in the semi-direct product decomposition. Therefore, S squared is identity. Okay. What next? Oh, and also the way theta acts on H is the same as S hat acts on H, because the way phi acts on H is trivial, because H is abelian, so it doesn't have any inner automorphisms. Okay. So let's decompose H as H plus and H minus. Here theta equals 1. Here theta equals -1. And let's consider this X here, from which phi is constructed. So X can be written as, and also note that this is the same as to say that instead of theta, let's just write S hat. So we can write it like this: 1/2 X plus S hat X plus 1/2 X minus S hat X. Right? This guy lies in H plus, this guy lies in H minus. So introduce U, which is just the first half here, and then let's write V as not what you would expect. This is going to be just -1/2 of X. It doesn't lie in H plus or H minus, it's just something in between. So therefore, we can rewrite X as U plus S hat of V minus V, as you can verify. But then apply the adjoint. The adjoint of X is the adjoint of U, and then the adjoint of S hat of V, and then minus the adjoint of V. Now, if you apply some automorphism to an element of the algebra, and then apply adjoint, this is the same but also, just for technical purposes, let me here write minus inside. So this is the same as S hat, then the adjoint of V, then the S hat inverse. This is pretty easy. But now S hat is an involution, so we can just ignore the -1. Okay, but now let's apply the exponential map, because remember that phi where was it? I guess I didn't write it here as an equation. Phi equals this. So if you want to get to phi, this is the exponential map of add x. So let's apply the exponential map. Now H is abelian, so the exponential map is a morphism of Lie groups. It takes plus to multiplication. So here we can just write exp ad u plus, sorry, just multiplication. I should take exp of this whole thing, but if you take a matrix, then conjugate it, and then and take the exponent, this is the same as to take the exponent and then conjugate. That's linear algebra. So we can here just write s hat exponential of ad of v, and then s hat, and then the exponential of ad of v inverse. I took minus as an inverse. So this was our phi. Okay. Now I introduce psi. I take it to be this thing. This is why I introduced you in the first place. So take it to be this. Now, here's the equation we need. Let's consider s hat psi s hat. Just by rewriting psi and taking these two s hats inside the exponent the way we did the opposite kind of here, so we can do it kind of backwards. This is just the exponential map of add of s hat u. But look, u lies in h plus. On h plus, s hat is identity. So s hat of u is just u. So in the end of the day, this is just psi. Okay, so now let's bunch all of this together because we're pretty much done. Remember that psi, oh sorry, theta was phi s hat, except let me just make kind of retrospectively one, it doesn't really change anything in the proof except for some details. So I wrote theta as phi s hat. Instead, again, it changes nothing else in between, but I want it to be s hat phi just for some, otherwise I would have to swap a few factors, and I don't want this. Let's make let's write it as s hat phi. We can do this as well because symmetry decomposition works in both ways, but nothing else changes in between, literally. And then here we also write it as s hat phi. So, and now we use the formula for phi. So this becomes s hat, and then we use psi. S hat psi, which is this guy, s hat, the exponential of ad v, s hat, the exponential of ad v inverse. Now, this is just psi. Okay. And now I finally want to claim that I can swap psi and this thing, they can just interchange them. Why? Well, because psi is the exponential map of ad of u. and H was abelian, so U and V commute, so their adjoints commute, so their exponents commute. So I can literally just, this guy can swap places. And then we call this theta1. So we've shown that theta is conjugate to theta1, which is now psi s hat. And now I claim that this is the same as s hat psi. Why? We already used it actually. Psi is this. Let me actually pinpoint the exact location where we used it. I think you can, it's the same as this formula. Because you can put s hat here, and s hat inverse is the same as s hat, so it's pretty much the same formula. Okay, so now I claim that this is what we want. So we wanted to show that theta is conjugate to something, which can be decomposed as s hat, and this guy of the form x of ad of something of special with special properties, which I'll show you again in a second. Now we just need to finish with this psi and to show that it has the properties that we want. Let's see what we want. We wanted to write theta up to conjugation as such a thing, where s hat is what we want, and then psi has the following property. It can be written as the exponential map of add of this guy, where all roots are even on t, or just even integers. So let's go back. So psi is this guy. So write u as pi over 2 it. Then psi is what we want. So left to show that every root is even on this thing. This is equivalent as to say that alpha of u lies in ei z. As you, this is because u is pi over 2 it. Okay, so let's show this. Well, we know that theta square is identity. Therefore, psi squared is identity. Well, let's take psi squared and apply it to some e alpha. Remember that e alpha, sorry, so let's take this guy. By definition, this is this. Now, if you take the commutator, if you apply add to e alpha, this will be just multiplying e alpha by some complex number, precisely alpha of 2u. So if you take the exponential of add of 2u and apply it to E alpha, this will be the same as to multiply E alpha by the complex number, which is alpha of 2u. But now psi squared is identity, so this is just E alpha. Therefore, alpha of 2u is in 2piz, which is the same as to say that alpha of u is in piz. Any questions here? Are you still with me?
Yeah.
And we're pretty much done because part 3 is, I mean, straightforward. So we're left to show that this θ1 commutes with our 3 guys, with the compact real structure tau, with the split real structure sigma, and with the Weil involution omega. So u, look, all roots are real on T, which is now we know the same as all roots are purely imaginary on U, right? So U lies in I HR. Remember that HR is the real span of all root vectors, which is precisely where all roots are real. Because all roots are imaginary on U, it lies in IHR. And if we go back, remember that we had U, G was U plus U minus. Here we had H, and this was H0 plus IH0, which is HR. So IHR is just H0. H0 is this, and U plus, where H0 lies, is where the compact real form. So what I'm saying is that tau of U is just U, because U lies in U plus. But because tau of U is U, it follows that tau times psi is the same as psi times tau. Because, well, this is just because psi is the exponential map of add of U. Okay, now sigma of U is minus U. Why so? Sigma is the split real form. The split real form is identity on HR and minus identity, well, on IHR. So sigma is -1 on this thing, therefore sigma of U is minus U. But this means that sigma psi sigma is psi inverse. But psi inverse is just psi, because psi square is identity. So therefore, sigma psi is psi sigma. And omega is just the product of tau and sigma. Therefore, omega psi is psi omega. Okay, and this is, I think, it.